we will consider in general elastic body, and so I want to give a refresher of the theory for the modeling of elastic body within the linear elastic theory, but in the general framework of finite element analysis. So this is the content of today's lesson, and so I start this argument, these topics, by turning on the code of the lesson. Okay, and so last time I have introduced to you the standard representation for an elastic body. Here he has a flexible member, like a wing, a member, and for X I'm indicating the position in this frame of reference here, and so X is the position, and C, like C1, C2, C3, so for alpha running from 1 to 3, are the current material coordinate. The material coordinate in principle are arbitrary coordinate representing the material point of the of the flexible body. In general, the representation of the motion is giving us the position here, the position X as a function of time in any time for any material point. And this position is the sum of the reference position. Typically, the reference position is corresponding to the undeformed configuration for the flexible body, plus a displacement. This representation is also known as referential representation of the motion, in the sense that you represent the motion with respect to this reference configuration. And this is the displacement. Here I have, for a time, take a picture of this deformable wing, and we have the green reference configuration here with the green meshes, and the red one representing the deformed configuration. Okay, so we have the X vector, which is the sum, which is actually the sum of the reference vector like this. This is X0, like this. So for the point we have X0, which is the placement of the initial position of the material point, plus the displacement moving the initial position of the point to the deformed configuration. So this is the rho of the displacement U, which is the small vector, black vector here. So the sum of this long vector plus this small vector is the final vector giving you X. Okay, but the unknown of the structural dynamic problem is actually U, which is the displacement. A focal point of our position is the approach of the approximated solution, or the representation of the solution in a set of new coordinates. The new coordinates are currently the Lagrangian coordinate Qn. Note that one introduced a couple of objects, which is this shape function and this new coordinate. You have a couple of actors. The first one, the shape functions, are functions which are given by the designer, by the engineering. So I have to choose this function in order to represent time by time, for each time, the solution in the space. So these are shape functions to be decided. And the Qn are the corresponding coordinate. Now I want to focus on very standard choice for this shape function or for this corresponding coordinate. And the choice is the choice which is typical of the finite element discretization. However, before introducing this discretization for psi, I want just for a second to suspend this discussion on the psi function and related QN coordinate. And I want to suppose with you to know this function and this coordinate assumed just for a second. If you assume this structure for the solution of the problem, and if you are able to express all the kinetic energy of the elastic body indicated like T, and all the elastic energy of the flexible body with capital E, like this. Next, the equation of the motion can be expressed in terms of this new Lagrangian variable in this way, by this equation here, also known as the Lagrange equation motions of the flexible body. So you have potentially a set of new equations representing your body, your flexible body, in this new coordinate system, in this new, Lagrangian or unknown variable Qn. Another point I discussed with you the past time is the following, is a point about this material coordinate psi 1, 2, and 3. These material coordinates are in principle arbitrary, in the sense that you can decide to fix this material coordinate, for example here, by using a brush, painting your initial structure with the green line. So do this and fix also a numeration for this coordinate, like a scale for each line. For example, this green line here, you have the green line, excuse me, okay, you have this green line, this other here, this other here. So this green line, this direction are the, for example, the C1 direction, and you have C1 equal to 0, 2, and you fix this on this line here, and these other here are the green line like C2, C2 one value for C2, second value for C2, and so on. Okay, moving this other direction. So if you fix a couple of this C1 and C2, you have a point on the wing, a material point. If the wing is moving, this green line moves together with the body. So you are actually fixing for C1 and C2 a material point, and you are following the material point, okay? But the most useful and famous choice for this material coordinate is the following. Take the Cartesian position coordinate at the initial position for the body, so at the undeformed configuration. And take this as reference material point. And this is standard in structural dynamics. It's standard in structural analysis. Okay? And so from now on, instead of X1, X2, X3, we may use X simply. But remember that X is actually indicating the material location of that point, but in the initial condition. Just to fix the idea, consider the coordinate of the nodes in a finite element model. If you are working with the finite element model, you are the boss for deciding the coordinate of the nodes of your model. And that coordinates are the coordinates of the node in the undeformed configuration. Okay? However, you may have as output of your code the displacement of this. So that position will be displaced to another position. But the original node coordinate is representing actually the material coordinate. Okay? Okay. In other courses, for example, the courses of aeronautical structure, I will obtain the final equation of motion by using first principle. First principle. And for first principle, I have in mind the momentum equation for the elastic body, the constitutive relationship for the material, and the, for example, the kinetic relationship relating the strains and displacement. By using this set of equations, you have a PDE complicated model for your elastic body, and then you can resolve this problem in so-called weak sense, not strong, weak sense. And by solving this problem in weak sense and assuming this position here, which is the same, this position, one can obtain the final equation of motion, which is this equation here. Now I want to propose to you another approach, an energetic approach. So defining kinetic energy, elastic energy for the body, the energy associated to the law, and then apply a minimum of the total energy for obtaining our final equation. And this is another alternate approach, but is quite identical. Okay? So now the objective of this discussion is the following. Try to express the total kinetic energy as a function of the new coordinate, Q and Qn dot. Express the total elastic energy as a function of new elastic energy, a new elastic Lagrangian variable, and then apply this equation, also known as Lagrange equation of motion. You know this equation for a rigid body dynamic. You studied this in your rigid body dynamic course, in previous course, like Meccanica Razionale is mathematical model for engineering.
Yes.
Okay. Okay. So, but this is valid also for elastic body. This is the new announcement for you. Okay? And we can apply this equation as a stationarity condition for the total energy. And in corresponding to the stationarity condition for the total energy, you will find the solution of your problem. Okay? By imposing the stationarity. And this is the new approach I want to propose to you to find the same equation. So this is my promise. I have to just to express the kinetic energy, the elastic energy, and then assuming this, apply the Lagrange equation of motion. Apply, so assume these two, this third, and assuming this, apply Lagrange equation, and then obtain this. This is the step, okay? Before applying this procedure, let's discuss this. What is the meaning of this? Look, I'm using X instead of C, okay? By intending that X is position, but in the initial configuration, okay? Equal to summation of psi and X, Q and T. What about Q? What about psi and so on? Okay? Just a brief discussion on this. And the first point is psi, X, and are shape functions satisfying the body boundary condition. And point dot, they are requested to be independent function. In the X domain. What does it mean? Instead of clarify this point, I prefer to do directly a practical example of psi function and the corresponding Qn function. And this is the case of finite element discretization. In fact, once one defines psi n x and corresponding Qn, comma, one is actually defining the space approximation of the structural problem. Better, space approximation after truncating the summation. If you define this function psi and truncate this summation here, you are currently approximating your problem. So this is almost equal to, not identical to. But you have to take independent function such that to span all this space X of your problem. I want to be clear. After truncating the summation. This example is very standard. I am discussing on the meaning of this. And I want to define the space approximation known as finite element approximation. What finite element approximation means? I want to show this with an elementary one-dimensional continuous problem for a linear elastic line, also known as a beam, for example, an elastic beam, straight beam. If you have a straight beam, you have this reference configuration. You have a unique C1 or X1 axis, and you have your beam here in the undeformed configuration. The length of the beam is L. And in the deformed configuration, if the beam, for example, is a cantilever beam, you have something like this. Okay, this is the deformed configuration for the beam. And this is U X in a time, in a fixed time, T bar. Okay? This is the continuous definition. And this is the U component. And X is the X domain. You don't have vector for u, you don't have vector for x because we're one-dimensional with one-dimensional component, a double one-dimensional. Okay? So, simple case. What finite element means? Finite element means, please divide your domain in finite element. Okay? So, for example, consider this, this, and this. So we have 1, 2, 3, 4, 5 finite elements. Okay? And consider 5 nodes, in this case, like this, the first one, the second one, the third, the fourth, and the fifth. Okay? And introduce the following 5 psi functions. First one is psi1. Psi1 means a psi of x function of this type. This is 0, and then this function, the value of the function to the node number 1 is 1, and then 0 to the other nodes. So it's a function like this. The value here, the node is the node 1, this 2, 3, 4, and 5, and this is the value here is 1. Please define all the other functions in the similar way. Psi2 is a function of x with values the Italian mathematician called this function funzioni nulle quasi ovunque. These functions are almost always null function on zero value function, and they assume a different value by 0 only in a special value of the domain. This is the idea, this is the practical idea to have a base function for your problem, a base function, independent function. Okay, this function I am going to define are a very characteristic way for defining independent function. This is 1 in the node number 2 because this is the function number 2, and 0 everywhere. Okay, this is 2, 1, 2, 3, 4, and 5. The psi3 is 0 everywhere, but not 0 in 3. Okay, so we have 0 here, 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 and here. We don't have 0 in 3. Okay, and finally you have psi4 and psi5. Please write, complete this scheme. Now the question is, what about ux at the time t bar when you combine and sum psi1, you know psi1 now, by q1 t plus psi2 at the moment this psi2 is not a vector, but because we have a scalar value function, psi2 as a function of x by q2 t plus or the other. So I want to sum this function, this function, this function, and imagine to have a linear trend between the 1 value and 0. So imagine to have a straight lines connecting the 1 value with 0. So if you sum this, the final result should be a linear piecewise function, connecting the node values. So as a final result, if you are agree with me, we should have something like this, this, and this, but connected by straight line, because you have used straight function going from 1 to 0. But if you used different connection line between the 1, 0 and 0 value, 1 value and 0 value, you should obtain other trend for connecting the point on the node 1 with the point red in the node 2 and so on. But in this case, our approximated function, the approximated function is this here. After this summation, you should have the red line like this, 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 this. And ladies and gentlemen, this is the finite element approximation of our analytic function. This approximation is depending on the structure of the function I have decided to use for connecting the value 1 with the value 0. Okay, another point. Can you interpret the meaning of Q1, Q2, Qt as a function of time? And here we have this value at, excuse me, t bar, because we are fixed in the frame t bar, the picture T1, t bar. So the value of this quantity is exactly the amplitude of the shape solution in the node. So we have this value, this blue value, this here, this here, this here, this here as a negative value, and this here. This blue value are the meaning of Q1, Q2. So the new Lagrangian variable of my problem in the finite element framework or approximation are currently representing the displacement of the structure in specific nodes of my discretization. Okay, so I want to suggest to all of you, I already did this, but I am refreshing your brain, and I am giving this information for people who does not know me in previous course. So I am giving to you the finite element vision of the continuous elasticity problem. In the finite element framework, the Lagrangian variable, if you introduce the shape function this way, are currently representing displacement in this node of the structure. Once we are define your shape function are tenth or head function. In the literature you can find the nomenclature head function or tenth function. And if you introduce this function as function going from 1 to 0, necessarily this structure is giving to you this representation of your solution. For example, look, if you consider your solution from the node 2 to the node 3 here in this interval of space, you have that here, you can consider in this interval from 2 to 3, you have the combination of this and this. All the other shape function do not give any contribution. And so, if you sum this yellow function, which is a part of psi2, with this yellow function, which is part of psi3, and you combine, multiplying psi2 by q2, but q2 is the value of your deformation here, and you sum this contribution by psi3 multiplied by q3, you should have this final red approximation. Okay, and this is the meaning of finite elements. So any kind of designer, engineering design, structural design, start by this finite element discretization. And I want to convince all of you today, tomorrow, the day after tomorrow, that if you assume by a code this kind of approximation, and you are working with a linear elastic body, necessarily you will produce as a final equation for your problem this model here, this kind of mathematical model here. And therefore, you are currently moving from a partial differential equation in space and time model to a ordinary differential, linear ordinary differential equation of second order, only in time. And this result is quite general. For any kind of continuum you are working on, spin, plate, 3D, elastic body, everything. Okay? And this is the point, the basic point of structural dynamics for working with an elastic problem. Okay? So this, after this position, after this comment, now we can start on defining this function t as a function of, it's possible to define this kinetic energy as a function of q and q dot in order to be able to take this partial derivative here. And this is the first step, the further step we are going to do. Well, what about the kinetic energy? The kinetic energy for the body is the old definition of 1/2 the integral on the body domain rho velocity dot velocity dv, kinetic energy. But what about v? I know that u is, with my position, equal to the summation of psi n qn, and therefore u dot me, which means v, should be equal to psi n x q dot n. Okay, and note that I can use equal almost if we truncate this and take a finite number of Lagrangian variable, which means a finite number of finite elements. Excuse me for this kind of expression, a finite number of finite elements. So a space discretized representation of my model. Okay, so if we include another comment, if you have a vector for the displacement, you should consider a vector field of shape function consistently. In the previous case, we have a scalar displacement function or a component, and then we have scalar shape function, only one component. But if you have a problem in the space, the scalar functions are associated for any direction. Okay. So here in the general case, we have a vector field for velocity, and that this vector field of velocity is approximated by this expansion of function. Remind that I told you that this function are respecting the constraint, the boundary conditions. Okay, boundary condition means that all the shape function has to be 0 here. If you have a cantilever beam like here, all the psi 1, psi 2, psi 3 chosen has to be 0 here. And so when you combine many functions which are all 0 in that point, you are expecting the fact that your solution is 0 in that point. Okay, if you have non-homogeneous boundary condition, we can fix this point. Okay, but in general, for this initial approach, we're assuming that all these functions are homogeneous functions in the sense that are able to respect the boundary condition, the zero boundary condition at the boundary. Okay, so kinetic energy, we have this, and therefore we can write this like the integral of, for V, I can write summation of n quantity q dot nt psi n, function of x, dot the same velocity, but this expansion, the second expansion, the second V is independent to the other when you take a square of a function. These two expressions have to be independent. So we have to use another index, please, for emphasizing this point. This V is independent to this other, and then you have to construct, you have to build this V, you have to build this V and then take the product. So this building process is independent. Okay. Dot mt psi m x dv. And so this kinetic energy is 1/2. We have a double summation of m n q dot m q dot n out of the integral, because this integral is a space integral, not in time. And we have psi n x dot psi m x rho, which is a function of x in general, if you have a not homogeneous body, for example, dv. Okay, so once you have fixed m and n, you have a constant here. For any m n, you have a quantity like this, which is mn. And this coefficient are able to describe a table of number which are currently defining a mass matrix. This is known as also as mass matrix. Okay, and this, if you consider this algebraic discretized definition, so here you have equal if you take infinite contribution. If you take infinite finite element, you have an exact rebuild of your model. But if you consider a truncation, finite element, this is almost equal to this. So this kinetic energy is almost equal to 1/2 q dot transposed t by the mass matrix by q dot t. Okay, and what about, look to this kinetic energy. What can you say about the kinetic energy? The kinetic energy is a physical quantity of your deformable body, and for any state, a state means velocity. For any velocity field, this quantity is greater than 0. How can you recognize this property? Here, look, this is the modulus of the velocity. The positive quantity multiplied by the density is a positive. So integrate a positive quantity, you have a positive quantity for any kind of V field, for any kind of velocity field. So this quantity is intrinsically positive. Impose this property in the discretized form. Can you ask, how can you ask that this quantity be strictly always, how can you ask, how can you recast this quantity be greater than 0 for any state? But now, what about the state? In the continuous variable, the state is the velocity field V. But now, the state is the Qn quantity. Is represented by the Qn dot quantity. Okay? So, this means that, this implies that the kinetic energy is greater than 0 for all Q dot vector. discretize vector for any q dot. And if you request to a matrix to give positive value for any of these, you are requesting to M to be positive matrix. The definition of positive matrix, indeed, is the following. A matrix is positive if and only if you take the matrix supposed to be positive and pre-multiply this matrix by a vector and post-multiply by the same vector for any vector A, if the matrix is strictly positive, you should have a positive number. This is the definition. And this definition is quite compliant with the definition of kinetic energy, and then induce ourselves to decide that our mass matrix has to be positive matrix in the strict sense. In the sense that if you take, the definition is for all A not equal to 0, this quantity is greater than 0. Okay? Okay. Note that positiveness implies symmetry. However, this matrix is symmetric because, look, you have this scalar product here. What is it? Oh my God. You have this scalar product here, and if you exchange the role of n and m, you have the same quantity. So m is equal to mn is equal to nm. Because if you exchange here the role of this function, you are actually applying the commutative property of the dot product of scalar product. Okay? Okay. So this is what I can say about this. And finally, we can now take this derivative here and this derivative here. In particular, the derivative of t with respect to Qn is 0, because our kinetic energy for this kind of elastic body in the neighborhood of undeformed configuration is not dependent on Q. Probably in your previous course in mathematical models, when you worked with the Lagrangian equation of motion, you, for example, the classical pendulum or double pendulum, something like that, you have the possibility to have a kinetic energy depending also by Qn. But in this case, we have all the dependency on Q dot n. Okay, so we have 0 here in this part, but if we take the partial derivative of t with respect to Q dot, we have to consider this. And how can we take this derivative? We have to take this derivative, and we have a double summation here of, look, in order to take this derivative, I have to use, please, different notation for the index in the summation, okay, for brain health. So double summation of R and S quantity, just to take strange index, and I have to summate this to add this R M R S Q dot S. Okay, when I take this derivative, I have to derive this quantity with respect to this position and consider the other constant, and then this reverse, derive with respect to this, and consider this other constant. The message is the following: the derivative of x squared, you know, is 2x. Why? Because you have the derivative with respect to x of x by x, and you can derive with respect to this, taking the other constant, and then the reverse. So you have the derivative of x with respect to x is 1, so you have 1 by x plus the derivative of the other with respect to x is 1, and then you have x by 1. Okay? This is trivial in the case of the function, but is essential when you have algebraic quantity like this. And therefore, when you derive this with respect to, and here you have r equal 1, 2, 3, 4, summation. You are deriving with respect to the nth q dot. So you have 1 when you are lucky and you are considering r equal to n. In the other case, 0. Okay? Therefore, you are, in the first derivative, you are currently suppressing the r summation, and you have to frozen the r summation when r is equal to n. Okay? And so you have 1/2 summation. The only summation survived is s, and you have 1 by m for r equal to 1, and s is summing currently q dot s. Finished. Plus, I have done this. Plus another summation. Okay. Now I have to derive with respect to this other here. Okay. And here I have r. Excuse me. Yes. Okay. And now I have to sum with respect to this other position. Okay. And therefore I am running with r. And we have m r s. Excuse me. M r1. Excuse me. And we have 1, and we have q dot r. Okay? Now, apparently, we are summing different quantity, a summation, another summation. But the question is, are we summing the same quantity? The answer is yes, we are, because the matrix is, excuse me, is not 1, is n, or excuse me, is 1 here, but instead of 1, I have n, excuse me, this is n, and is n. Okay? Excuse me. But this summation in S and this summation in R are summing the same quantity because the matrix is symmetric. Okay? And so I can collect in a unique summation 2 times, and this 2, which is this 2 here, look, this 2, which is this 2 here, is able to cancel this 1/2. And so the final result is the following: a unique summation, for example, S summation, summing M and S by Q dot S. And this is this derivative. And finally, and I'm concluded my lesson. And finally, taking this time derivative, I have that at the end, the derivative with respect to the time of the derivative of t with respect to q dot n minus the derivative of t with respect to q dot, excuse me, qn, but this term is identical equal to 0, is the summation of S, for example, quantity M and S q dot dot s double dot s. Okay, so this term of the Lagrange equation of motion is exactly this term here, in general, where the mass matrix is given by this. And I have concluded my lecture today, where the mass metric is this definition here. Okay, tomorrow we obtain the last part of the equation, so demonstrating that any kind of elastic, linear elastic body can be represented by this equation. And in particular, if you use the shape function as done by the finite element approach, the corresponding meaning of the Lagrange variable is displacement in the node point. And this is an advantage in an engineering point of view. Okay? Thank you. See you the day of tomorrow.